All right. Yeah, give me a next slide if you guys need it. Otherwise, let's start this thing up. Go ahead, Melissa.
Okay, so this is a progress presentation on our project, Atlas Acrobatics. I'm Melissa, and I'm with Max and IEEE. So just to reiterate, our project objective is to simulate Atlas doing various acrobatics, shown in the image here. So some feasible results that we want to achieve by the end of this semester are to demonstrate offline trajectory generation for acrobatic motions, and to play back these trajectories in RViz so that you could see Atlas in various stages of an acrobatic maneuver in RViz. And then we want to test our controllers by introducing noise to test their performance. Our stretch goals for this semester are to implement our controllers in PNC and to simulate Atlas in the simulator performing acrobatics in real time. So this is our planning control pipeline from the last presentation. We want to start with creating our projectile motion trajectories, then feeding those trajectories into our optimization, which will happen offline using Centroidal dynamics and whole body kinematics. And then we want to feed these into our model projecting controller and our whole body impulse controller. So this is the current status of our trajectory planning. You can see in the figure on the right, we've plotted the center of mass, which is shown in the black circle with the cross, jumping from a lower position, performing a flip in the air, and then landing on a higher position. We can use this to estimate takeoff and landing velocities and to then estimate ground reaction forces based off of the velocities. So most of the constraints for the optimizer are fairly straightforward to derive, except for the angular dynamic constraints. Specifically the ACAM matrix, which gives us this nice equation that maps our joint rates to our system angular velocity. And this ACAM matrix can be derived using various transforms of our system inertia and our Jacobian. So to further go into these transforms, the paper that I'm basing this off of has this neat little chart, which have 3 different spaces. We have our joint space, which have our joint rates, which can then be transformed into our system space using a Jacobian. So this system space has the velocities and angular momentums of all of the rigid body lengths. And these are then transformed into the center of mass space. Next slide. And so the values that we're particularly interested in are going from our joint rates Q dot to our system momentum, or our center of mass momentum HG. And we want to achieve that by deriving the AG matrix.
Awesome. So next we're going to go into some of the groundwork we've laid. Essentially, we decided to derive our own forward kinematics and Jacobians for Atlas symbolically in MATLAB rather than trying to interface to another program like PyBullet or MATLAB. And having those symbolic matrices is really powerful because we can look at them and extend them, and having them as pure math is very powerful essentially. So we can look at them and extend them any way we want, and because we can take the Jacobians and Hessians and provide those to optimizers. So I'm actually going to show some examples. So this is the ERDIF that we've got out of RAS, and you can see the ERDIF for Atlas. There's a couple subtrees, but it's generally pretty straightforward. So in MATLAB, we can load the ERDIF in, and it constructs it as a rigid body tree object with all the joints and links. It's something that you can access as like a standard MATLAB thing. We can load up the robot in a variety of configurations and look at it, look at the joints, see what axis they rotate about, see what their names are. Next up is code that we actually wrote. So we traverse that ERDIF tree, and this is essentially just printing out inertial values at each of those links to show how it traverses it. But also behind the scenes, we are calculating the symbolic transform to both the joints and to the center mass of each link. And when we do that, we can then see what joint variables are those transforms dependent on and take the Jacobian with respect to those variables. And so what this results in, and this is now me typing, is we have a map or a dictionary, and you can look up a link. So I'm going to do the right clavicle, for example, and we have the joint transform, the center mass transform, the Jacobian, the center mass Jacobian. And if we look at one of these, joint transform, this is a 4x4 homogeneous transformation, and it's completely symbolic in terms of those joint variables. And we can evaluate it at any of those parameters that we need. Similarly, let's look at the Jacobian, and that's a 6 by I think 33 matrix, also entirely symbolic. So the last point that we did was we actually generated random configurations of the robot and then compared our symbolic solutions to MATLAB's numeric solutions to validate them and verify that our math is correct, but while still maintaining that like symbolic aspect that we have. So there's a lot of power there. So moving into our trajectory generation, a really important reference for us was called An Introduction to Trajectory Optimization, How to Do Your Own Direct Collocation by Matthew Kelly, 2017. The author now works at Boston Dynamics on trajectory generation for Atlas. So that should tell you how that went. It's about a 50-page paper that goes through a lot of broad concepts as well as really specific implementation details. It was super helpful to us. So we're looking at direct transcription methods, and essentially we want to take a continuous optimal control problem and formulate it as a discrete, like finite size nonlinear program. So the dynamics are only enforced at knot points. And so what Kelly describes is that you can use spline interpolation between knot points to approximate the continuous solution. So you can see on the right, these like they have using like linear interpolation between the knot points. We have like a so-so estimation of the true optimization we're going for. And then on the bottom, by applying instead quadratic splines, the final estimation ends up being a lot more true to life. And so using this spline interpolation allows us to basically get a somewhat continuous function out of our trajectory optimizers. And then if we have an NPC or another process that runs at like a different discretization step, we can just subsample it or sample it in whatever way. We don't have to worry about like those conflicting sizes. So another question we've been facing is how to deal with multi-phase trajectory generation. So something we've realized is all of the hard constraints essentially are like constant through all 4 phases. So the Euler integration obviously is through all 4 phases. The centroidal dynamics, which has a lot of like the nonlinear aspects like Melissa spoke about in the ACAN matrix, is constant. The joint kinematics are complicated and they're constant. The only thing that actually changes in terms of the constraints is in the flight phase, the contacts and reaction forces are different. And that's not too difficult to like formulate. So essentially, multi-phase optimization, we have all 4 of these phases in one single NLP, and it adds a flexibility at those transitions as opposed to just stitching individual phases together, because instead of having to specify explicit end conditions for each phase that is like the start condition for the next phase, we can leave that up to the optimizer essentially. And that allows it to have a little bit more flexibility. Another aspect that we've been like kind of researching and looking at is the idea of a keyframe. And essentially, from what we've read, we want to separate the concept of a keyframe from a knot point, because if we enforce dynamics at knot points, we could have 100 knot points throughout this trajectory that we generate. But in terms of like an animation keyframe where we want to guide it through some points, we might only have six keyframes here that we actually care about corresponding to each of these pictures. So essentially, if we take 6 or so knot points and weight them really high compared to the rest of the knot points, it guides the trajectory through those points without having to explicitly specify the intermediate actions between them.
So after we receive the optimized trajectory, the next step is how to follow this design trajectory. As mentioned previously, there are 3 phases, the takeoff, flighting, and landing. And among them, flighting is relatively easy. It just basically follow the optimized trajectory, because when it's in the air, we can simply set the PD controller of all the joints to the designed joint space values and as well as the torque values. And for both the takeoff and the landing phase, whole body impulsive control is required. This controller is basically set the task into different prioritization. And through this process, it can be realized the safe takeoff and the landing at the same time. The model predictive control here plays role to generate a desired body posture and the ground reaction forces. This is very important when do the landing, because the kinematic energy are supposed to be dissipated to the ground, so that the setting of the body posture and the ground reaction force is very important. Next slide. The whole body impulsive control here applies for both takeoff and landing phases. I have finished more than half of the coding about this part, but there are still some bugs, so I cannot demonstrate the result here. But basically, the inputs that we get are mainly from the optimized trajectory, except the last one, the ground reaction force is generated by MPC calculation, and we have to measure some state variables as well. There are basically different kind of Jacobian functions and the real-time joint space values. And as a result, after going through this WBIC process, we will have joint position command, joint velocity command, and torque joints, the torque of the joints. There are basically two processes of the WBIC. The first one is prioritize text execution. We set the body inclination, which is the Euler angle of the body, as the first task. Second one is Centroidal momentum. This is applied to follow the track of the trajectory. But the third one is the most important for following the trajectory, which is just simply follow the center of mass of the robot to follow the design trajectory. After going through this process, we will have the command of joint space, and among them, position and velocity will be input to the PD control directly, but the acceleration will be inserted into the QP solver to find the joint torques, and all these values will be inputted into the PD controller. Next slide. The model predictive controller is applied for the landing, because I also have down the code about this part, but similarly there are some issue at this moment. But basically, what this controller do is trying to find the minimum value of a set state space, which is X here. The theta is this value basically defines the body posture, and the F defines the ground reaction force. Next slide. The last one is the flighting phase. This one is pretty easy. We just directly input the joint space values from the optimized trajectory, and the acceleration of the joints will be inserted into Lagrange equation to calculate the torque corresponding to each joint, and this value will be inserted into PD controller. Yes, that's the end of it.
All right, awesome. Thanks everybody. And I guess I'll end this Zoom and make sure that this recording came out fine, and then I will submit it. So, yep. Cool. I will end this, and if for something's wrong with it, I will text you guys.